All right, now let's move on to the quotient rule. So looking at the quotient rule, again, intuitively I would think, oh, this just means to take the derivative of the top function divided by the derivative of the numerator. That's what I would think to do. But let's see if that's the case. So if f of x equals x to the 7th and g of x equals x cubed, does the derivative of f of x divided by g of x equal the derivative of f of x divided by the derivative of g of x? I don't know, let's try. So d over dx is, so x to the 7th over x cubed. Okay, properties of exponents, that's going to simplify to x to the 4th power. And now I can actually take the derivative, so that gives me 4x cubed. All right, when I look at doing it the other way, that would be d over dx. Oops, let's do this in a different color. D over dx of f of x over d over dx of g of x. So that would give me 7x to the 6th in the numerator over 3x squared in that denominator, which gives me 7/3 x to the 4th. These are not the same. So we cannot just take the derivative of the numerator divided by the derivative of the denominator. So the formula for the difference quotient, or the quotient rule, excuse me, the formula for the quotient rule is as follows. It is the function in the denominator times d over dx of f of x minus f of x times d over dx of g of x all over g of x squared. Again, if you want to write that with less letters, it would be g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. Let's go through and check this with this problem now. So if I were to do this now, all right, so if I were to find the derivative of x to the 7th over x cubed the long way. So this is obviously the shorter way to do it, is simplify. If you always can simplify what's in there and not have to use quotient rules or product rules, obviously do that. But let's just say we didn't see that we could do that, and let's apply this formula. So our g of x is x cubed, our f of x is x to the 7th. So it is g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. So that's going to give me x cubed times 7x to the 6th power minus x to the 7th times 3x squared all over x to the 6th. So that becomes 7x to the 9th minus 3x to the 9th all over x to the 6th power. So that gives me 4x to the 9th power over x to the 6th power, which becomes 4x cubed, which is exactly what I needed it to be. So again, you can see this took a lot longer than what I did here. So what I always recommend students do is when you're dividing two functions or even multiplying and finding the derivative, first see if you can actually simplify the quotient or product and then apply derivative formulas. And if you can't, then go through and do these quotient rules and product rules. Let's look at an example using the quotient rule. Differentiate y equals e to the x over x. Okay, so I have two functions getting divided by each other, e to the x and x. I can differentiate e to the x, and I can differentiate x. I can't differentiate this quotient, though, without using that quotient rule. All right, so derivative of y with respect to x is going to equal, so using that quotient rule, so it is the derivative, so the second function, it is the denominator, so g of x, so there's our g, there's our f. So g of x, which is x, times the derivative of f, minus f times the derivative of g, all over g squared. So that's going to give me x, e to the x, minus e to the x times the derivative of x is 1, So it's just going to be e to the x times 1, which is e to the x, all over x squared. Let's look at another example. Differentiate g of r equals the quantity r minus 1 over the quantity r squared plus 3. So we can see this, we're going to have to use the quotient rule for this problem. So the derivative of g equals, so it's the denominator, so the quantity r squared plus 3 times d over dr, so the derivative of the numerator, which is r minus 1, minus the numerator, which is r minus 1, times the derivative, so d over dr, of the denominator, which is r squared plus 3. And then that's all over the quantity r squared plus 3 squared. Okay, so now let's do each of these derivatives. So this is going to give, so I still have r squared plus 3 multiplied by the derivative of r minus 1. Well, the derivative of r minus 1 is just 1. And then minus r minus 1 times the derivative of r squared plus 3, which is 2r. And then this is all over r squared plus 3 quantity squared. Distributing things through, we end up having r squared plus 3, and then minus, I'm going to just do the product first. So r times 2r is 2r squared, negative 1 times 2r is negative 2r, all over the quantity r squared plus 3 squared, which equals r squared plus 3. I'm going to distribute that negative through now, minus 2r squared plus 2r, all over the quantity r squared plus 3 squared. And now I can combine like terms, and I'm left with negative r squared plus 2r plus 3, all over the quantity r squared plus 3 quantity squared. Okay, let's look at this one. So this one, oh my gosh, it's a little more complicated, right? We have products, we have quotients, we have so much stuff. We have e to the x's. So let's go slowly. So the first thing I see is that I have two things getting divided by each other. So we're going to start with the quotient rule. Okay, so we'll call this our numerator function, so our top function, and we'll have this one be our bottom function. Okay, so let's first set it up that way. So using that quotient rule, so the derivative of the function z with respect to x, because x is our function here. Okay, so that's going to be the denominator, so the bottom function times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Okay, so let's just work this through. So I get x to the fourth minus 1. Okay, so to figure out this, that's the derivative of two functions getting multiplied together. So I'm going to have to use the product rule here. Okay, so to differentiate those, that's going to be the first function times the derivative of the second plus the second times the derivative of the first. Okay, I just did it in that other color just so you could kind of see where that's coming from. I'll actually just keep the parentheses in purple. So in that case, this is where I had to go through and use that product rule because I can't actually figure out what the derivative of x cubed e to the x is without using that product rule. Okay, and then that's going to be over, or subtract e cubed, or x cubed, e to the x times, so the derivative of x to the fourth is going to be 4x cubed minus the derivative of 1 is just 0 because that's a constant. And then that ugliness is all over x to the fourth minus 1, quantity squared. Okay, so then that's going to become x to the fourth minus 1, and that entire quantity, so don't forget your parentheses. So that's getting multiplied by x cubed, the derivative of e to the x is e to the x, plus e to the x, the derivative of x cubed is 3x squared. So now I found that derivative. And then when I simplify this second term out, I'm going to get 4x to the 6th power e to the x all over x to the 4th minus 1 quantity squared. Okay. Now, if you wanted to, you could kind of go a little bit further. It doesn't simplify anymore, but if we wanted to, we could kind of make it look a little cleaner. I can pull an e to the x out of both of those terms and an x squared out of both of those terms. So if I factor that out, an e to the x and an x squared, I'd be left with an x plus 3. And then I still have this minus 4x to the 6th e to the x all over x to the 4th minus 1 squared. And this just ends up getting pretty yucky when you go all the way through, so we're going to leave it right here. Let's look at an application. Let the function v of t equals 6 times the cube root of t all over the quantity 4t plus 1 be the volume in centimeters cubed of a balloon at time t in seconds. Find v of 8 and v prime of 8 and interpret both in the context of the balloon with units. So the first thing we'll do is let's figure out what v of 8 is. So v of 8 is just substituting 8 into the original equation. So v of 8 equals 6 times the cube root of 8 all over 4 times 8 plus 1, which gives us 6 times 2 over 32 plus 1, which is 12 over 33. So what does this mean in the context of the problem? Well, it means at 8 seconds, the volume of the balloon is 12 over 13 or 33 centimeters cubed. Okay, so now let's look at what v prime of 8. So to find v prime of 8, the first thing that I need to do is figure out what is a formula for v prime of t. So let's find that derivative formula. So v prime of t equals, so we're going to use the quotient rule here. So the denominator 4t plus 1 times the derivative of the numerator, so d over dt of the cube root of t, minus the numerator, so 6 cube root of t, times the derivative of the denominator, which is 4t plus 1, and then that's all over the denominator 4t plus 1 quantity squared. Okay, so figuring this out, I'm left with 4t plus 1 times the derivative of 6 times the cube root of t. So remember, I could rewrite that as 6t to the 1/3 power. So using that power rule becomes 2t to the negative 2/3 power minus 24, minus 6 times the cube root of t times the derivative of the quantity 4t plus 1, which is 4. And then again, this is all over the quantity 4t plus 1 squared. Okay, so we could keep on going and simplify more, but we actually are at a point where we can just, now that we have this derivative formula, we can substitute in 8 for t. So v prime of 8 is going to equal 4 times 8 plus 1 times 2 times 8 to the negative 2/3 power minus, I'm going to just combine the 6 and 24. So 6 and 4. 6 times 4 is 24 times the cube root of 8. And then again, that's 4 times 8 plus 1 quantity squared. All right, so substituting that into your calculator will end up giving us in the numerator, we get negative 31.5 0.5, and then in the denominator, we get a value of 1089, which is approximately negative 0.0289. So now if we're needing to interpret this and make sure that we're using units, what does this mean? So remember that a derivative is the rate of change. Does it make sense that this is negative? So let's see. V of t is the volume, and so this looks like, so our volume, the rate of change of the volume at 8 seconds is decreasing. So this means this balloon is deflating. And we could say that, so the rate at 8 seconds, the volume of the balloon is decreasing at a rate of negative 0.0289 centimeters cubed per second.